So today I'm going to talk about the second to last topic in the course, which is binary search. And then we have one more topic after that, which is sorting. And that's it. That's not bad. We have 5 more lecture periods and several labs, 5 more labs. And we have just these 2 additional topics to get in there. That means after going over these topics, we'll have time to review and help get you prepared to do well on the final exam. Okay? And also to help you complete the labs and the assignments that are remaining.
Were we going to finish part 3 of lab 7?
What's that?
Were we going to finish part 3 of lab 7?
Part 3 of lab 7. Did I start that? Vector insertion. We can do that. Actually, I can fit both of these in today. Okay. So let's do this one. So the problem for part 3 is to implement an insert function. And here we have a vector that has elements that are in sorted order. And here's an example, 3, 6, 7, and 12. These are in ascending sequence. And we want to write a function called insert. And it takes a vector v as the first argument and an integer k as the second argument. The function inserts k into the vector so that it preserves the order of elements. So here's a test case that's given right here in the problem. There's an example. And we have those 4 numbers, and then we need to insert an 8. That means the 8 goes between the 7 and the 12. Don't use the insert function that's already a part of the vector class. So we're going to reinvent the wheel here. And use, as in all the other similar problems, we're going to use assertions to write test code. So let's take a look at that. So we have an insert function, a vector v, and it takes an integer k, and it will do something, I don't know what. And then we have main, so we create the test code. Let's go ahead and look at that. Let's use the test code given in the problem, 3, 6, 7, and 12. So we will insert the values 3, 6, 7, and 12. The size of the vector should be 4. We'll leave that out. And then we'll call insert and pass in the value 8. And when we do that, the size of the vector should increase to 5. And we should get the values 3, 6, 7, 8, and 12. So at this point in the program, v equals 3, 6, 7, and 12. No, not to use the, this is what I'm asking you not to use. That's what I'm asking you not to do, okay? Don't call the insert function that's part of the vector class. Instead, implement your own version of insert. But actually, this insert, that's not, I'm not familiar with the insert function of vector class. I don't remember it, but I would guess that there's like a position that, you have to say that it should be at a position. And so this insert function would, in fact, be used, no, not that one. The insert function wouldn't appear here. It would be in here somewhere. So we don't use insert in here. Do not use a v.insert. Does anyone know? Is it so? I want to insert, say, I think you need to provide a position. Is that it? So I don't remember. So I'm not sure about the form that insert takes on the vector class. We'd have to look that up. So after we do the insert, after we call insert here, the resulting vector should look like that. The size will go to 5, and so on. Okay, let's run the test code and watch it fail, and we'll check where will it in fact fail. We don't need this test. This was something that we used to validate our understanding of the vector class at an earlier point in time. I'll take that out. So we insert 4 values. We check that the size is 4, so that check should pass. Then we call insert, and we check that the size is now 5. So let's make that fail. And I'm just going to comment that out. So the insert function doesn't do anything now. So size is not 5. That's what we expected, because our function stub doesn't do anything, doesn't increase the size of the vector. Okay, so now what we're going to do is find a place for the new value. We're going to find a place for the new value and put it there. So that we just some idea here. We're going to need to look through the vector class, the vector itself. We'll need to. I'm just roughing it out here. We're going to need to do the vector. And we can do this using a linear search to find the right spot, or we can use a binary search and find a spot. So if the vector was small, we don't need to do a binary search. If it's just a few items, then we could simply look at each one after another, find where the number goes. But if the vector is very large, we can do better than a linear search. We can use a binary search. And a binary search means to look in the middle. We look in the middle, and we find out, well, is the middle, is the value we're looking for bigger or less than the value that's in the middle? And if it's bigger than what's in the middle, then we look to the middle of the upper half. And it's like looking up a name. It's like looking up a word in a dictionary, a manual dictionary, right? An old-fashioned dictionary or an old-fashioned telephone book. I don't know if people use those anymore. I don't, but I used to. Has everybody in here used a telephone book? You used to get them at the house and you just toss them in the recycling bin, right? That's what we do. But anyway, if you want to look up, huh? So, you know, if you did want to find a name in the book, the names are sorted in alphabetical order, just like the numbers in this vector. And so, just to be practical, to search for a name, you're going to jump inside somewhere. You're not going to look at the first page and then the second page and the third. That would be inefficient. You're going to jump in the middle and say, well, did I get there? You know, maybe I'm looking up, say, Jones. And I'm looking for the J's, and I open up the middle. I say, oh no, that's an M. You know, that's a Martinez, and so I got to go to the left. So I toss out the right half of the phone book. We set that aside. We take the first half and we split that in half and see, well, you know, am I before or after the J's? And you keep searching, and that's called a binary search. That is much more efficient than a linear search. I mean, you can imagine 1,000 pages in the book, and you look at page 1, page 2, page 3, you know, and you're looking for Jones. It doesn't make sense. So, but what we're going to do is not make sense. I'm going to suggest that we keep it simple because it's easier to do a linear search, and then after we do it this way, then we'll do the more complicated one, which is the binary search. We'll do that next. So what I mean by search, we're searching for the place to put the new value. So let's scan through the vector and look for a good place. So we'll do it like this. We'll say, you know, we'll start at 0, and we're going to say, well, what's at 0? Well, let's look at, well, what's at I? So I ranges from 0 to the end of the vector, and if k is, if we find it, well, let's do it like this. So if as we look through the vector, right, what we want to do is see that when we want to find where k ends up being equal to v of I. And then we'll take action there. But maybe we hit a value that's greater than k. So actually what we want is k less than or equal to v of I. Because here, look at our example. We're going to look at, this is v of 0. V of 0 is 3. V of 1 is 6. V of 2 is 7. And V of 3 is 12. Oh, V of 3, 12 is bigger than or equal to 8. So this is the slot where we want to put 8, and we want to push 12 to the end. So this is not very good test code. So we'll create more tests. And I got this wrong here. This is less than or equal to. So here we found the spot where we need to put the value k. But what we need to do is shift everything to the right from that point to the end of the vector. So let me just do that. So we'll start at, maybe we'll start at the end of the vector. Let's do it like that. Let's see if I can explain this to you here. So we've got our vector. Here's the algorithm that I'm going to propose we use. So here's our vector, and we found that it needs to go here. So what we're going to do is create a new spot in the vector, and we'll copy values into it. So we'll take this 12, and we're going to copy it into here. And then in the next action that we take, we're going to write the 8 over top of the 12 that we just copied out. Those are the two steps we're going to do. Actually, the test code is not that good. I want to, and 8 is okay. Let me improve the test code here so it's easier to explain the algorithm. So we'll have 5 elements. I'm just adding a 15 on there. So at the end, the result looks like that. That's correct. Oh, I'm sorry. Size is a 6. So let's add a 15 here. Let me show you the algorithm from this perspective. So we have a 15 in there. So we append an empty slot onto the end of the vector. Let me start over. We append an empty slot, a slot on the end of the vector. And then we start moving the values into it. We're going to copy 15 into here. So we're going to position a pointer. Actually, I'm working out the algorithm in my head now. So we'll append onto the end of the vector, and then we'll position the pointer here at one before we did the new append. And we check this. Actually, leave the pointer here. We'll check the previous number. If the previous number is less than or equal to the value we're inserting, then I'm just going to write it right in there. But it's not less than or equal to, it's not bigger than or equal to the previous value. So what we're going to do is going to copy the 15 into that slot, and now consider this as the possible location for the 8. But we won't have removed the 5. Oh, we could do a swap. Why don't we do it like that? Maybe that's easier to understand. Let's take you append the 8 onto the end, and if that value is less than the value that precedes it, then we swap. We swap the 8 and the 15. There we go. That's going to work. And then we're going to compare, now we've got this pointer to the 8. We're going to compare 8 to the value before it. That's a 12. So that means we're going to do another swap. So 8 and 12 get swapped. And now we compare 8 to the value before it. Oh, now 8 is larger than or equal to the value before it, so we're done. That's the algorithm that I will use. And I'm going to completely redo this thing. And I'm just going to implement what it is that I showed you just now. I take the V, I use pushback to put the value on the end of the vector. Now we've got a situation that looks like this right here. Now we're going to swap the 8 with the value that precedes it, as long as 8 is smaller than the value that precedes it. We'll go like this. So while v of k, or actually we could do while k, we could say while k is less than, oh, we can't do it like that. We need an index here. We'll call it I. I'll call it the position of k. The position of k will be v dot size minus 1. The position of k, we need to track the position of k. And while k is less than v of the position of k minus 1, that's the value that precedes k, we're going to swap, we're going to swap like that. We're going to swap v of position of k minus 1 with the v of the position of k. So look here, we put k, which is 8, we put it onto the end of the vector. And then we make a record of where k is. So we declare a variable called position of k. And it's in the last slot in the vector. Well, look here, the vector is of size 6, okay? The vector is of size 6, but of 8 is not 6, because counting starts at 0. Indices start at 0. So the size of the vector is 6, but the position of the last element is 5, index 5, because indices start at 0. That's the reason I subtracted 1 here. So there it is. We have a variable to track the position of where k currently is. And now we have this condition. I'm going to write this in a way that I think makes it easier to understand. V of the position of k, that's where we put k. We put k, in the end, in the beginning. And so now V of position of k gives us the 8. And we want to compare that value with what's in the position just to the left of it. And that's the index position of k minus 1. So if the thing before it is bigger than the thing, then the thing is out of order. And that means we need to swap those. So how do you swap that? When you go V of position of k, that gets, the one before it, basically. So the thing that comes earlier, we copied into where we stored the 8, where we stored the k. And then, and the thing that we just, and then we're going to move the 8 down into the earlier slot. So we can do it like this, because actually k is stored in the variable k. We're not modifying k, so. One more thing to do. Anyone want to suggest what we do next? We have a loop here. If we don't do anything now, we're just, see, we have an adjusted position of k. Let's decrement position of k. Because see, position of k is no longer the location of where k is anymore. We put something else there. And we put the k at an earlier position. Oh, so let's decrement the position of k now, so to make sure that's correct. It's pointing still at the, it's equal to the index of where k is stored. And then we sit in the loop. So the first time you pass through this line right here, actually I'm going to, when we enter the program, the vector looks like that. So let me line these up. When we first enter the program, the line looks like that, and then we push back k. So now the 8 is on the end. And then we swap it with its predecessor as long as it's smaller than its predecessor. As soon as it's larger than its predecessor, we stop. That's the algorithm. And this almost works. It works for the test data that we have. At least I think it does. But I think that I can create a test that makes this fail. But let's just, and I can create a special case test that makes it fail. But let's just worry about the general case. And we're developing for the general case right now. Then we'll handle the special case next. Let's see if this works. See the problem? Can everybody read? Everybody should be able to read this error condition and fix the problem. Who sees the problem? Should be pushed back. I spelled it wrong. Oh, it's hard to read, isn't it? Okay, it's hard to read. It does give us line 15. It says error class std, that's the standard namespace, ::, vector int std allocator. I know that's really hard to read, so you just have to gloss over that a little bit. But you know they're talking about the vector class here. This vector class has no member named pushbash. So stuff that you don't understand. All right, so it's up here. We got a compilation error. This should be pushed back. Oh, v of 4 equal 15. That's. That's right, thank you. So the test code is wrong. This should be a 5.
And then up above it, several lines should be pushed back 15.
And I should be pushed back 15. Thank you very much. That's correct. Here's the error. The test code is bad. Now let's try that. All tests pass. Is it time to move on to the next problem? I don't think so. Is there a test case that we can come up with that makes this thing fail? Huh? Let's try that. Let's try that. And look, I'll tell you, we're going to end up modifying our code, okay? So what we want to do is we want to preserve our existing test cases. Okay? So we don't want to lose, and that's a principle of software engineering. It's bad to throw away good test cases. You got to keep your old test cases around. So let's create a new vector, call it v2, and let's push a 3, and maybe a 6, and then let's call v2 dot insert 16. That was the suggested number. Is this the stress test that you want to give it? Like insert something that goes on the end, right? Want to try this one? So this should give us. Let's do the test. I'm going to grab this. It's a little dangerous to copy this code here, but I'm going to do it anyway. I just have to remember to change v to v2. I'll do that first so I don't forget. That's v2. So the first one should be 3, the second one should be 6, and the third one should be 16. That's the way we want it to work. Let's try that. Oh, what is going on? I'm not even going to read that. What did I do wrong? Oh, v.2.insert. Now, look at that, see? I'm breaking the rules. I said don't use that. Okay. That's it right there, isn't it? That's how it looks. The insert function takes the vector with the value to want to insert. Okay. All tests pass. Is it time to move on to the next problem? Can anyone think of a test that's another test we ought to do before we move on? Yeah, that's a good test. Let's try the same number. That's a great test. Let's do this. And I'm going to copy that. That's an excellent test. Let's put in a 3 here. Everything's going to be a 3 now. I'm going to make this change throughout. So instead of 16, let's insert. Well, do we want to match against the first one, the second one, or add another one and match against the middle one? The general, you know, to make it general, we want to match against the middle one, right? So here we'd want to make it 16. So the ends are special cases. So we're going to, but what we're testing is whether matching works. So let's test whether matching works in the general case, when we're matching against an item that's in the middle. That doesn't look right. So let's see, 3, 6, and 8, and we're inserting a 6, so we should get 3, 6, 6, and 8. Is that agreed? That's good. All tests passed. Is it time to go home yet? We should try to stress it some more. Any other stress tests you want to think about? Let's see. We tried the standard case, which is a vector with no duplicates. And we we inserted somewhere in the middle. Then we did another case where we had a vector of no duplicates. We inserted a matching element somewhere in the middle. That worked all right. But we could try a vector that has duplicates. Maybe that doesn't work. But you know, I think it does work. Does anyone see the test case that's going to reveal the flaw? No one sees. Okay. Maybe there isn't. Maybe it's done. Maybe I'm wrong. Let me try to create a test case that crashes. All right, vector 4. And I'm going to push back 3, 6, and 8. And then I'm going to insert a 2. Maybe this works. I don't think it does. So this should be 2. Now I'm inserting a value that precedes everything. So that's 2 and 3 and 6 and 8. Say it again. Thank you. Thank you very much. Really appreciate that. I lost my focus, and I missed that. All right. Anything else we need to do? So we're pushing it. We want this thing to go into the front, right? So, in other words, we're going to be, at a certain point, position of k will be 0. Position of k will be 1, say. Will be 1. And v of 1 will be 2. And then position of k minus 1 will be 0, and then v of 0 will be 3. And so this condition is true because 2 is less than 3. So we're going to swap the first 2 items, the 2 and the 3, and then we're going to decrement position of k. Now position of k becomes 0. Position of k becomes 0, and now v of 0 is 2, because we put it there. But what is v of 0 minus 1? What is v of minus 1? Well, that's an illegal index. So there's a bug. There's a bug in the program. And I don't know exactly what's going to happen. I think it's going to be a segmentation fault or something like that. Okay? We're going to get undefined behavior. In another language, I want to let you know, they do range checking. And the runtime will say, oh, illegal index. You cannot use minus 1. That's what most languages will do. They use range checking. But C++, that language does not do range checking. So the behavior is undefined. So we're just going to have to see what happens here. That's one reason why development in C++ as a language is more difficult than other languages, because of that feature and others as well. Okay, let's see this. It compiles, but it's not a compilation error, it's a logic error. Oh, it works. I was afraid that was going to happen.
What if the number you're going to insert is already bigger than the one that before?
See, the value before here is probably a 0. I'm going to make this fail. See, because we're accessing memory that we don't know about. So the result is undefined. Okay, the result is undefined. And what's happening is it's poking into memory in a place that we're not controlling, and it's finding a value that's less than 2. So it stops. So we're going to make it crash because we're going to put in a -2. I think it's finding a 0. So if we put in a -2, I think we're gonna get what we need, which is an error message. So we insert the -2. That means the -2 should end up in the front, right? Here we go. And sorry, I didn't mean to cut you off back there. Let me get back to your suggestion. Got it. Wait, no, I didn't get it. The assertion needs to be fixed. Oh, so I did get it. See, what happened is it indexed into memory, and it got something that preceded the first element in the vector and swapped it with the -2. And that's why the assertion failed. Can I get back to your comment, whoever made it?
If you insert like, say like in 17, then you would just
if I insert it as
like if you were just to insert like now we're inserting an 8.
Yeah.
If we insert like a 17, then we have to tell the program just to leave it at the end, not to swap it.
Yeah. Yeah, but isn't that working already? Did we test that or not? We tested it here. We tested it right there. So the code, the way the code is written, it already works. Because watch, I'm going to explain that. Look at the algorithm. Well, thank you for bringing this up, by the way. This is a very good question. We had, what did we have? We had it looked like this. Is that right? And so in what the algorithm does, look here. The first thing we do is we push back k. So if we were to push back 17, then we're all set. So does it work? Does that all setness get properly processed in the code? Let's say we're going to push back k. K is bigger than the last item. Calculate the position of k. Well, okay, that's just the last index, no problem. And then we say, well, you know, while the thing before k, which is 12, well, that's bigger than k, which is 17, well, that's false, right? 12 is not bigger than 17. So the condition in the loop is false from the outset. That means we never enter the loop. We skip over the loop and we just return from the function. But the problem is, when k is at position 1, and it's less than the thing that's at position 0, and we swap it so that k goes into position 0, we're all set at that point. That happens right here. But then we adjust the position of k to 0, and then we continue with the loop and try to look at position -1, and that's where we get messed up. So we need to add an extra condition here. While position of k is greater than or equal to 0 and the position of k minus 1 is greater than position of k. So we need to have that extra check to handle the edge case, where the value gets inserted into the beginning of the vector. Now, we ran it before, and we got a test code that failed here. Let's run it again and see if we fix the problem. We didn't fix the problem. Huh? Oh. Thank you. It's not coming out. What is the issue? Oh, no. There's the problem right there. We're accepting position of k to be 0. But when position of k is 0, position of k minus 1 is negative. So I got the wrong expression there. So it should be, position of k must be strictly bigger than 0 so that position of k minus 1 is bigger than or equal to 0. Sorry to cut you off back there. Did you want to follow up on that? No? Okay. Okay, all bets here. Who thinks it's going to work? This is the moment when I feel totally confident. I think it's going to go. Okay. $1, 10 to 1 odds. I saw a hand back there. No, I got it. I win $1. Okay. Anyway, is there... Now, here, the thing is, it's all about the test code. You know, so you really can't... There's a lot of skill in developing test code. And like the test that I thought was going to fail succeeded when I used 2. And I had to think and say, no, 2, you know, I could have just said, oh, yeah, it works well. But then I realized, you know, that what was going on, so I tried a -2 so I could get it to fail. So it's really tough. It's pretty tricky to actually come up with good test code, and it's impossible to do. So what you need to do, you can't just rely on test code. You really need to think through the algorithm and understand it, reason about it, and prove it to yourself. You know, with like type of a mathematical proof to verify, you know, intellectually that the algorithm is correct. And then use as much test code as you can to verify the correctness. And if you're designing, you know, the space shuttle and you have code that's going to operate the space shuttle, you're going to write a lot of extra tests, right? But if you're designing a video game or you're incrementing some player's character level, you know, how many tests do you need for that, right? So someone didn't get their character leveled up. Well, you know, maybe you lost a customer, but you didn't crash the space shuttle. So, you know, that's something to keep in mind. You know, what's the right amount? You got to be judicious about what you put into your test code development. All right, so let's move on. So here is problem 3 of, I'm sorry, this is binary search. Did I do that right? Yeah. This is binary search. And you know, we don't actually have time to do this. We have, okay, after today, we have 4 more lectures. So what I'll do in the next lecture is cover binary search at that point. And then we have 1 more quiz, right? 1 more quiz. So that means we have 2 more lectures. Huh? When is the quiz, by the way? Is that coming up? Next Wednesday? Like 2 days from now?
No, the following Wednesday.
Oh, the following Wednesday. Oh, and we cover binary search as well. Okay. You know, binary search is everywhere. It's easy to look up. I will cover it on Wednesday. I will cover binary search on Wednesday. And that will help you get ready for the quiz on the following week. So we don't have any days off, do we? We don't get Thanksgiving off in this class. Sorry. All right, so, huh? There should be a bonus for that.